Alrighty, my friends, I have a killer exam problem for you for thermodynamics in your general chemistry class, and it deals with enthalpy change of chemical reactions. And we're going to do a couple warm-ups before jumping right into the exam problem. So this is the first warm-up here, and I do recommend going through these warm-ups and not just jumping straight to the killer exam problem, just so we know all of the nuances and are ready for it. So we have this chemical equation here, and this is the first one. It's an equilibrium reaction, and we're given the enthalpy change. Now this superscript here means it's in standard pressure. Standard pressure, and standard pressure is 1 bar, so this is occurring under 1 bar, this reaction here, and the enthalpy change is 57 kilojoules per mole. So if this occurred under constant pressure, then this would be the energy transferred as heat. It's positive, which means that we have energy going into the system. This is the system. Energy going into the system is heat, so heat transfer into the system, so it's getting hotter. And likely, it could be getting hotter anyways. And if that's occurring, then this is endothermic. Endothermic. So that means we need to put heat into the system. Now, we can't really put, heat isn't a thing to put in, but we need to transfer energy as heat into the system. So it takes energy for this system to go. So we would have like heat on this side kind of thing. Okay, now given this, we want to know what the change in enthalpy is for this reaction. And this reaction is basically the same, right? It's not much different. Just to go from here to here, what we did was we divided everything by 2. So if you divided everything by 2, then we do the same thing. It takes half the amount of energy as heat if we have half the amount of moles. And this mole here means per mole of the reaction. So for every 1 mole of N2O4 that reacts, we need 57 kilojoules per mole of energy as heat. So if we only have half the amount of moles, then our delta H naught is going to be half of this. So that's 26. I should be able to do this in my head. 28.5 to 2 sig figs. 28.5 kilojoules per mole. And this per mole now means, and same with this one, per mole. We didn't change the per mole, but the per mole means per mole of the reaction. So even though this is how many moles of this reaction occurs, it's really for a half a mole of N2O4. So this isn't per mole of N2O4. This is per mole of the reaction, which is half a mole of N2O4. So it's technically 28.5 kilojoules per half a mole of N2O4. This makes sense because if we kiss and flip this 1/2 and multiply this thing by 2, we get the same number here. This is very, very important. This is per mole of the reaction. And in this case, it's per half a mole of this. And this 57 would be 1 mole of this. Okay, all right, let's do the next warm-up here. We have this reaction, methane and water produces carbon monoxide and hydrogen, all gases. We have the change in enthalpy here. And now we want to know what the change in enthalpy of this one is. And what did we do? Well, we flipped everything, right? CO and H2 is now on this side, reactant side, where previously it was on the product side. And we multiplied everything by 4. You see everything by 4. So we did one operation. We flipped it. So we flipped the reaction. And when we flip the reaction, we got to flip the sign for this. So the change in enthalpy is now negative 210 kilojoules, which makes sense. So this, again, we have another endothermic reaction. If this top reaction required energy to proceed to the right, then in order to go to the left, it's going to release energy. That's why this is negative. Okay, so the next operation is we multiplied the coefficients, the whole reaction by 4. Therefore, we need to multiply this delta H by 4. So it's going to be 4 times negative 210 kilojoules, which is negative 840 kilojoules. Now, see, they just put the kilojoules here. Technically, this is kilojoules per mole of the reaction, which means negative 84 kilojoules no, negative 840, excuse me, not 84, that doesn't make sense, has to be a bigger number, forgot the zero, negative 840 kilojoules every time is released, every time 4 moles of CO reacts with 12 moles of H2. Okay, this is the start of our killer exam problem. Silver and chloride ions are mixed to produce silver chloride precipitate, and we have a balanced chemical equation here. And I'm going to pop up the first one. Now, there's a lot of parts here, but this covers a lot of material, so don't be worried about all these words here. You're going to learn a lot from this question, guaranteed. Okay, is this reaction endo or exothermic? This is kind of an easy one starting off. So the change in enthalpy is less than 0. See, it's negative here. It's less than 0, which means this is exothermic. So that's nice. We already talked about that one from the warm-up. Now we want to calculate the change in enthalpy for the formation of 0.2 moles of silver chloride. Now we have this, the change in enthalpy. This is per mole of the reaction. And whenever this reaction occurs, we have 1 mole of silver plus and 1 mole of chloride minus produces 1 mole of AgCl. So this is equivalent to negative 65.5, not 0.6, 0.5 kilojoules for every 1 mole of AgCl, solid. Because this is per mole of the reaction, and every time this balanced reaction occurs, we'd have 1 mole of AgCl here. We want to know how many there are, this change in enthalpy for 0.2 moles, so we multiply this point by 0.200 moles of AgCl. A lot of students would stop right here, but we need to incorporate the 0.2 moles here. Okay, so this is 65. I'll just plug it into the calculator. Negative 65.5 times 0.2, 13.1, negative 13.1. So negative 13.1 kilojoules. So this is the change in enthalpy. This is the energy transferred as heat away from the system because it's negative when this many moles of AgCl react. Now for the next one here, calculate the mass in grams of silver chloride deposited if we have this much energy is released as heat. So this is our change in enthalpy. That's what that is. The change in enthalpy is 1.00 kilojoules, and we want to know the mass of this deposited. So we need to know, we need to convert things around. So this is our change in enthalpy in terms of heat, but we want to know how much heat per gram there is. Now we don't have heat per gram, but we do have heat per mole, which is this conversion right here, which is based what we're given, the change in enthalpy, negative 65.5 kilojoules per mole. So we're going to start off with this number here, 1.00 kilojoules, and we need to know how many moles are produced by this many kilojoules. So we're converting units, and we want moles of AgCl. We want to cancel out kilojoules, and for every 1 mole of AgCl, we need negative 65 point, is it 65.5? Yeah, 65.5 kilojoules. So our kilojoules cancel out. Now we know how many moles we need, but we care about the mass. So we need to convert moles to mass. We want grams, and we want to cancel out moles of AgCl. It's always nice to say what it's moles of, so we make sure that AgCl cancels out with AgCl. In this case, that's really all we're dealing with, but we never know. Molar mass of AgCl, let's see what that is. AgCl, 143.3. So 143 point, did I say 3 or 2? 40.3, 0.32. Okay, then our moles of AgCl cancel out, and we're left with grams, and that will give us how many grams we need. So we'll plug that into our trusty calculator, divided by negative 65.5. I put parentheses here because I don't want this to look like dividing and subtracting. Okay, 143.32 is negative 2.188. Negative, oh, not right, negative 2.188 grams of AgCl. And we have 3 sig figs here, 3 sig figs here, a lot. So we have 3 sig figs. So negative 2.19 grams of AgCl. That's how much, that's, wait a second. Why is this negative here? Oh, you know what? We can't have a negative gram. See what I did? So this is how much energy is released. So this is released is energy lost. So that means this has to be a negative here. We need a negative here because this is energy lost. So negative and a negative, that cancels out to give us the positive number. Okay, so we need 2.19 grams of AgCl. Okay, last part of this killer question. Calculate the change in enthalpy for the formation of 2.5 grams of AgCl. So we're going from mass to enthalpy, and we're going to use the same thing. So we'll start with what we're given. We could actually do this using unit analysis. Grams. I'm gonna cancel out. I'm just going to not include the AgCl since we're not changing compounds doing stoichiometry. 2.50 grams, and we need to convert to delta H, right? But the only thing we have for delta H is the 65.5 kilojoules per mole. So we need to get to moles. So we'll go from grams to moles. We have moles here, grams here, and for every 1 mole, the AgCl is, just double check, 143.32. 32 grams. So our grams cancel out. Now we have moles of AgCl, and we want we don't want kilojoules. We don't want moles, and we don't want kilojoules per mole. We want just straight up kilojoules because we want this here, delta H. So we want moles to cancel out. So we wanted the denominator. We want kilojoules, and for every 1 mole that reacts, we release negative 65.5 kilojoules of energy as heat. Okay, we'll plug that into our calculator. 2.5 divided by 143.32 times negative 65.5. And it's a negative number, which is good because we're still releasing energy as heat. Negative 1.1425. Negative 1.1425 kilojoules. We have 3 sig figs. So negative 1.14 kilojoules is released. And does this make sense with the last problem? The last one was a little bit less. So we needed less grams of AgCl. See, this is about 2.2, which is less than this. So we should have less energy as heat. We released 1 kilojoule, where here we released 1.1. So it's a little bit more. So that's great. This one's a little bit more grams, so we have a little bit more energy as heat released. Cool beans. Sweet. Awesome. Okay. Hope you enjoyed it. I know this was a longer explanation, but I hope explaining everything really helped you, and I hope it'll help you for your midterms and final exams and all that kind of stuff. I got tons of other thermodynamics videos and other chemistry, math, and physics and all that stuff. So check those out. Thanks again for watching. See you in the next one. All right. Cheers.